Hi class, we're continuing with water in chapter 4, and we've already talked about water's unique ability to form hydrogen bonds and the properties that result from those unique abilities. And now we need to talk about water vapor in the atmosphere, which is what we call humidity. So humidity is the amount of water vapor, and remember, water vapor is just water in the gaseous phase or gaseous form. The humidity is the amount of water vapor that's in the air. And there are a few different ways we can measure this. We can express humidity as absolute humidity, mixing ratio, vapor pressure, relative humidity, and dew point. And all of these are telling us something about how much water vapor is in the air. So let's go through each of them. We'll just talk about absolute humidity and mixing ratio really quickly first. They're very similar, a little bit different though. The absolute humidity is the mass of water vapor, so how many grams or kilograms are given in a volume of air: cubic centimeter, cubic kilometer, cubic meter, cubic foot, right? A liter. So how much mass per unit volume? Mass of water per unit volume of air. So that's our absolute humidity. Our mixing ratio is very similar, except instead of saying per unit volume, we're saying the mass of the water in a unit of air compared to the remaining mass of dry air. So we have so many grams of water per so many grams of dry air. So it gives us grams per grams or kilograms per kilograms, mass per unit mass. So that's the difference between absolute humidity and mixing ratio. So now let's talk about vapor pressure. Vapor pressure it's actually like a measure of pressure. So what is the amount of the total air pressure that is coming from the water vapor content in the air? So if we have a box with some water, and in this case over here we have dry air. In this case, dry air means no water vapor. So in this case we have 0 for our vapor pressure with our totally dry air. Same temperature here, but now we've actually had some evaporation occur, and then we know there's also some condensation. But the net result is that we have some water molecules in their gaseous form as water vapor, and so that vapor pressure is now increasing. And so there's some amount of the total air pressure that is coming from those water molecules in the air, and that's what we measure as vapor pressure. So if water content goes up, vapor pressure goes up. If absolute humidity goes up, vapor pressure goes up. If mixing ratio goes up, vapor pressure goes up. So all three of those will increase if we have more water vapor in the atmosphere. Now, there's another condition that we need to be able to explain and before we can do relative humidity, and that is the notion of the air being completely saturated or reaching the point of saturation. And this is when the air is at equilibrium with the water. And so we can't move any more water vapor into the air than we already have. So in this case, the same amount of water is evaporating, it is condensing. The water vapor in the atmosphere is no longer increasing. So we can't increase that quantity of water vapor in the atmosphere anymore. And we call that saturation vapor pressure. And a really important concept that we need to make sure we're really clear on is that saturation vapor pressure increases with temperature. So if we put a little Bunsen burner under our box of air and water, the amount of water vapor that will exist in the air at that point of equilibrium is higher if we're at 30 degrees than if we're at 20 degrees. So as we increase the temperature, we can have more water vapor in the air and have that water vapor be at equilibrium with the water. Now, something that gets a little confusing is we often say, and I actually find myself saying this sometimes, that the air can hold more water vapor at higher temperature. Now, that's really a misconception because the air isn't holding the water vapor. The water vapor is part of the air, and the concentration of water vapor at equilibrium is higher at higher temperatures than it is at lower temperatures. But I think sometimes we think of these containers of air that you could say that that container can hold more water vapor if it's at a higher temperature. So we have to be careful with that term holding, but sometimes that maybe helps us sort of conceptualize what's going on. a little better. So we can plot this, and remember, we can say express the amount of water vapor present as vapor pressure, mixing ratio, or absolute humidity. And in this case, it's mixing ratio, the grams of water vapor per kilogram of dry air. And what we see is we increase temperature. So our x-axis here is temperature going from minus 40 degrees Celsius to positive 40 degrees Celsius. Our saturation vapor pressure, or saturation mixing ratio in this case, increases with increasing temperature. So if we're at 20 degrees, the air is saturated if it has 14 grams per kilogram of water vapor, versus, let's say, if we're at 30 degrees, the air is saturated if it has 26 grams of water vapor per kilogram of dry air. So as we increase temperature, we increase the amount of water vapor that's necessary to achieve saturation. So that's a really important concept in cloud formation and in a lot of the weather processes that we're going to talk about. Okay, so now let's talk about relative humidity. This is another way of expressing water vapor content in the atmosphere. And what we're doing here is we're saying how much actual water vapor is there in the atmosphere relative to the saturation amount at a certain temperature. So a key here is that relative humidity is temperature dependent. So if we change the temperature, the relative humidity will change if we keep the same amount of water vapor. Okay, so let's look at these diagrams. We have 3 flasks, and notice these are all at the same temperature. Okay, so we're all at 25 degrees Celsius. And we have 1 kilogram of air in each of them. And in this first one, we have 5 grams of water vapor. And our saturation mixing ratio at 25 degrees Celsius is 20 grams. So that means if this were at saturation, which would mean we have that equilibrium, the amount of water vapor in the atmosphere is not increasing anymore, then we would have 20 grams of water vapor. So that ratio of 5 to 20 is 25%. So the air contains 25% of water vapor that it could possibly contain at 25 degrees Celsius. Now we'll open the stopper and we'll stuff 5 more grams of water vapor in. And now what we've done is we're at 50% relative humidity at 25 degrees Celsius. So now the air contains about half of the water vapor that it could contain. And now if we open it up and we stuff another 10 grams in there, so we have 20 grams of water vapor, now we're at saturation. The evaporation rate equals the condensation rate. The water vapor content of the air in this flask is no longer increasing. There is as much water vapor in that air as it possibly could contain at 25 degrees Celsius, and we say that we have 100% humidity and we're at saturation. So we have to be careful with relative humidity because it does change with temperature. Okay, so 100% relative humidity means saturation. If we add water vapor, relative humidity goes up. If we remove water vapor, relative humidity goes down. If we change temperature, we change relative humidity. So a decrease in temperature equals an increase in relative humidity. And why is that? That is because relative humidity includes saturation, vapor pressure, the saturation level of the air in order to calculate what the relative humidity is. And so let's look at this diagram here. So now we have our flask. We start with 7 grams of water vapor, and we're going to cool the flask. And so what happens? Our saturation mixing ratio goes where? Up or down? It's going to go down. Here we go. So we're going from 20 degrees Celsius to 10 degrees Celsius. So our saturation mixing ratio goes from 14 down to 7. So as temperature decreases, that saturation mixing ratio decreases. So that means as we cool, if we don't change the amount of water vapor, we move that air mass closer to saturation. So that means the relative humidity is actually going to go up. So at 20 degrees Celsius, the air is actually, it contains half of the water vapor that it could contain. The actual vapor pressure is 7 grams. The saturation content of water vapor would be 14. So it's at 50% relative humidity. If we cool it, 10 degrees. Now our saturation mixing ratio is 7, and the actual content is 7, so our relative humidity is 100%. That air contains as much water vapor as it can contain. Now, if we cool it another 10 degrees, our saturation mixing ratio is going to go below 7, and so what's going to happen? We're going to have condensation happen. So we're going to have to move water vapor out of the gaseous form into the liquid form in order to reduce that vapor pressure or mixing ratio in the atmosphere. And so now we're down to 100% relative humidity again. So the relationship between temperature and relative humidity is really important. If we look at, here's our daily temperature trace for spring day in Washington, D.C. So we start at midnight, and the temperature decreases till just before sunrise. Here's our lowest temperature. And then it increases to late in the afternoon, and then decreases again in the evening. And what happens with relative humidity? Well, if our absolute humidity or mixing ratio or vapor pressure remain the same, and we just change the temperature, we would expect to see a reverse trace of relative humidity, right? So as our temperature decreases, we move that air mass closer to saturation, and so our relative humidity is going to increase as we move closer to saturation. And so our highest relative humidity is going to coincide with our lowest temperature. And then as we're going to warm the air mass, now we're going to move that air mass further from saturation, and so our relative humidity decreases until we reach our lowest relative humidity at the same time where we have our highest temperature. So another metric for describing the amount of water vapor in the atmosphere is what we call the dew point temperature. And the dew point temperature is the temperature that we would have to cool an air mass to in order to reach saturation. So it's a measure of the actual moisture content of the air. So let's say we've got an air mass that's at 40 degrees Celsius and it has 5 grams per kilogram of dry air. So if we want to move that air mass to saturation, what we have to do is start to cool it, right? So we're right here, we're at 5, and we have to cool it. We're going to move that air mass. We haven't changed the amount of water vapor in the air mass. We're just cooling the temperature. So we have to cool it down to a temperature of 5 degrees Celsius to reach its dew point. And that is the dew point temperature for an air mass that has a mixing ratio of 5 grams per kilogram. So it's the temperature that we need to cool the air mass to reach saturation. So if let's say we had an air mass that has a mixing ratio of 25, when we start at 40, we need to cool it down to about 28, 29 degrees Celsius in order to reach saturation. So that is our dew point temperature. So notice there is a relationship between dew point temperature and water vapor content. If we move down this graph, we're decreasing our water vapor content. And because this curve is also decreasing, that means we're decreasing the dew point temperature. So we were up here at 25, mixing ratio of 25, and our dew point temperature was about 28. If we go to a mixing ratio of 20, our dew point temperature is 25. If we go to a mixing ratio of 15, our dew point temperature is 22. If we go to a mixing ratio of 10, our dew point temperature is 15. We go to a mixing ratio of 5. So now we've reduced the water content quite a bit, and notice our dew point temperature is all the way down to 5 degrees Celsius. So we went from 28 degrees Celsius down to 5 degrees Celsius. So if a low dew point temperature means a low water vapor content. So let's look at a map of dew point temperatures from September 15th, 2005. What is this telling us about moisture in the atmosphere? Well, down here where we have high dew point temperatures, and this is in degrees Fahrenheit, high dew point temperatures means high water vapor content. That's humid, uncomfortable conditions. So notice in our little chart, if we're up above a dew point of 70 degrees Fahrenheit, that is typical of the rainy tropics. If we're at 65, that's what's considered humid by most people. And if we're above 75, then we're into like oppressive humidity. So we're not quite there down here in the southeastern U.S., but we've got parts of Louisiana and Texas, and over here on the eastern seaboard in southern Florida, where the dew point temperature is going to feel like the rainy tropics. And that's a typical dew point temperature that we see in that part of the world. So, and then if we move over here into these really low dew point temperatures, then we're getting into much drier air. Notice 55 is the minimum dew point that we can have severe thunderstorms form. If we get below that, we're not going to see severe thunderstorm formation. So from this 55 line south and east, then we have potential for severe thunderstorms. So the rest of the U.S. then and into southern Canada here is not going to see thunderstorm formation. Dew point can tell us a lot about weather conditions, potential for formation of certain weather phenomena, and weather processes.